Thank you for the invitation. I'm glad to be here and to be able to talk to you about some recent work that we did. I'm going to shift gears a little bit now. This was great work that was presented before by Sangjim, and it was great to see the work on these humanoids. Now I'm going to talk a bit more on reinforcement learning and how to make it a bit faster, a bit more robust, hopefully towards being able to use reinforcement learning methods directly on robots more in the future. And the title's a bit longish, I'm sorry for that. I'm going to present a Q function decomposition that should enable faster learning, can enable more interpretable reward design, and also helped us to develop a model-free inverse reinforcement learning method, which I hope I will get to in the end, if time permits. So just real quick, let's jump in. Q-learning, has been shown to be applicable on a diverse number of robotic platforms and has shown success in learning real tasks and be adaptive. Here's some work from Thomas Harnoya and colleagues from RSS 2019, where they applied the soft actor critic on this Minotaur robot, training it on flat surfaces and then showing that it's adaptable to going over some rough terrain and things like that. Here's some work from Martin Riedmüller's group at DeepMind, where they had this scheduled auxiliary cost work where they showed that they could make a robot arm learn manipulation tasks from scratch with these very general auxiliary rewards, and that was also very cool. And then there's again from Thomas Harnoya and colleagues some work where they applied this little robot hand to learn to position a valve and things like that. So there definitely is a lot of potential for Q-learning based methods in robotics, but we're still kind of far away from being easily able to apply them for complex real-world robotic tasks. There are many reasons, but one important reason that we see and that we try to address is the low data efficiency and the lack of learning stability that is caused by stochastic transitions in real-world settings. Yeah, so you have lots of stochasticity through sensor noise, through actuator noise, occlusions that you might have, or because you might have to estimate your rewards from some sensors or in a data-driven way by estimating reward functions. And that can all introduce noise, leading to more noisy gradients in the optimization approach, and slower learning, needing more data, and so on. So so this increases the complexity of the value estimation, as I just said, because you have to propagate these noisy gradients through long temporal horizons in your optimization tasks. So what can we do about it? And I'm going to try and tie together three pieces of works that we did in the recent years. And the basis of it is a new composite value function estimation. We call it composite Q-learning that increases robustness and data efficiency. And building on that, I'm going to present briefly how to use a part of it for formulating more interpretable constraints in tasks where we have multiple objectives that we want to cover, and also I'm going to briefly show you how we used some of this composite value estimation parts to actually enable model-free learning in inverse reinforcement learning. So this is joint work with my PhD students Gabriel Kalweit and Maria Kalweit, and you can find the paper at openreview.net. And the idea is the following. So, our idea was that maybe we can actually try to decompose the whole Q function into different parts, namely a truncated Q function that only estimates the return for the first n steps of some target policy rollout, and also, a shifted Q function that will learn the remainder of the first n after the first n steps. Yeah, so we have these truncated Q functions. They just learn, a very short horizon, basically, and then we have these shifted Q functions which should cover the rest of it. And we came up with a consecutive bootstrapping scheme in order to learn this in a model-free way. So we combine the two, these truncated and the shifted Q functions, to give us a complete estimation of the true Q function, true value. So you can see that, you know, we estimate all of these different pairs of truncated and shifted Q functions. For instance, here we only, I mean, I'm going into detail in the next slide, but basically what we do, we first estimate only the immediate reward and all the rest after it with this first shifted Q. Then we learn how to predict also the next immediate reward at the next step, discount in the discounted way, and also shift it from there. And we always combine them to the full Q return. And what we can see later, what we will see is that by doing this decomposition, we will be able to use different learning rates for these, you know, truncated and shifted Q functions, which can have a pretty dramatic effect when it comes to the learning speed, as we will see. So let's first talk about the truncated Q functions. For some horizon n that we want to cover, this is a hyperparameter that we need to tune, and I'm going to say more about that later. We estimate n of these different truncated Q functions. The first, as I said, is just, you know, basically estimating the immediate reward function. That's what you can see down here. So the first truncated Q is updated by just, you know, the target is just the immediate reward minus the old estimate. And the other ones, you know, for any I that's greater than 1, we estimate, we bootstrap from these earlier Q functions, the truncated Q functions. Yeah, so the third one, for instance, will bootstrap from the second one and so on. But the target is calculated by using the full Q in the end. Yeah, so the maximization over the actions is using the full Q. So it's really the greedy policy with respect to the long-term return and not just some truncated return. So the horizon is limited for these truncated Q functions. And that's kind of nice because we, of course, it's a much easier learning problem. If we only want to, you know, predict the immediate reward or just one step or two steps into the future, it's of course a much easier learning problem than if we want to predict a very long chain of immediate rewards and this cumulative return as we usually do in reinforcement learning. So we can expect that these truncated Q functions will actually enable us to make quick progress in the beginning. And these shifted Q functions then can take advantage of that, that they actually don't need to care for the immediate rewards for some of the early steps, right? So these shifted Q functions, they're basically only covering the remainder of the rollout after the truncated Q function. Yeah, so if we have, you know, 5 steps of truncated Q function estimation, then from the 6th step, or starting from that 5th step into the future, we have this shifted Q function. And again, here we have a consecutive bootstrapping. And as you can see here, yeah, now we do not have immediate rewards here inside these Q functions. Yeah, so here we only estimate the discounted maximum value of the Q for the next state, basically. Okay, so this really skips the first n rewards and then just covers the rest of it for the rollout. And again, bootstraps with respect to the full Q for the actions. So these are action value functions that skip the first I immediate rewards for the shifted Q function I. And then we combine them together, the truncated and the shifted action values, to get representation of the full return. Okay, so Q is then composed of basically the immediate return and the immediate reward and the discounted sum now of the truncated and the shifted Q function here, minus the old estimate. There's some issues when you use function approximation here, because as you can see, there's, sorry about that, there's some circular dependency with these Q values here. So we need to regularize, and you can find all the details in the paper, of course. So just as a quick recap or intermediate summary, This full return is split into two parts: a truncated Q function for the first partial sum of n rewards, and a shifted Q function for the remainder of this full return. We do it completely off policy and without learning a particular model. Yeah, so we use consecutive bootstrapping, can stay model free. And you can look at it as a sort of generalization of the regular Q learning that we all know and many of us love. If all the learning rates for these different parts, truncated and shifted in the normal Q, are the same, then you are back to regular Q learning. However, you can also decouple these parts and then design these different parts somewhat differently, use different step sizes and so on. And I will show you the advantages of that. So I will first show you some tabular results, and then also some MuJoCo tasks, robotics tasks in simulation. So here, this is a little toy example with a stochastic chain. You have two actions, A and B, and different transition probabilities associated with different rewards. And the gist is that it's always better to take action A because it has an expected immediate reward of minus 0.8, and B would have minus 1.01. So it has this very small probability of getting a very high negative reward here. And what you can see here we did a little comparison of regular Q learning with different learning rates. Yeah, so 10 to the minus 3, very low and slow learning, as you can see. And by the way, so these three graphs, they're for the same task, but they have different horizon lengths. So here it's on the left, horizon length 200, 400, and then 1000 on the right. And you can see if we make it very small, of course, we get very slow learning. If we crank it up a little bit to 10 to the minus 2, we get a pretty good learning speed, but we don't converge to the correct value. It's too big in the end. And 10 to the minus 1 is clearly too big. We make very rapid progress, but then we're stuck in some local minimum here. And on the opposite, the composite Q learning that we are doing here, we can have different learning rates for these different parts. Yeah, so here I think we have 10 to the minus 2 for the full Q learning, for the full Q, 10 to the minus 1 for the shifted, and 10 to the minus 3 for the truncated. So even though we use a mixture of these, in the end we're very fast and we actually converge to the right value. Why does it help? Well, the intuition is that truncating this value to a fixed horizon makes the learning problem easier. As I said, it's easier to predict just a few steps rather than a very long chain of stochastic rewards. And also this shifting, skipping these immediate rewards and then bootstrapping from these earlier shifted Q functions. Of course, you need to maintain additional Q functions, but as we saw, you can use higher learning rates. And the intuition is that this is possible because, as you skip these first I rewards, you don't need to take into account their stochasticity. So only the variability of the next state needs to be considered and not the immediate reward. This is why you can, and we actually did some theoretical analysis of that as well in the paper, and which corroborates that. And empirically also, you can definitely use higher learning rates for these shifted value functions. And that makes it faster and more robust in the end. So here, really quick, some results for this composite TD3. So we used this Q function decomposition within the TD3 algorithm, and evaluated it on these three platforms in MuJoCo, the walker, the hopper, and the humanoid. We compared with vanilla TD3, then to TD3 with a higher learning rate, and TD3 delta, which is an extension of an algorithm that was presented by Romov et al. In 2019 that uses consecutive differences of discount factors actually, and also is similar in spirit to what we're doing. Okay, right, here are the results for these MuJoCo tasks. But mind you, with the 40% uniform noise on the reward function, right? So this corresponds to the same level as the highest, perturbed rewards in this Romanov et al. Paper that we refer to. And we wanted to just see, how robust are the algorithms with respect to this high level of noise in the rewards. And we can see that, well, if we compare our composite TD3 here in green with the vanilla TD3 with a higher learning rate, the highest that we used for composite TD3 here, and this TD3 delta approach, in all these three cases, the composite TD3 is able to clearly outperform the other approaches here. So that was nice. We were able to speed up and make more robust this TD3 algorithm, and it's of course applicable to any Q-learning algorithm in principle. It's just this Q function decomposition and this consecutive bootstrapping scheme which you need to implement, and you can use different kinds of algorithms for that. Now, for the second part, I wanted to show you how we used these truncated Q functions that you just saw, also in a different approach to enable what we call long-term action space shaping. Second. Oops. What's going on? Sorry. Can you still see my screen?
Yes, but I think not as you would like.
No, it looks very scrambled. Just a second. Let me reshare.
Please. Now we see it perfectly.
It's better now. Yeah. Okay. Yeah. Great.
Perfect.
So it's called long-term action space shaping. Again, joint work with my two PhD students, Gabriel and Maria, and also Moritz Werling, a collaborator from industry. This was presented at IROS just a few weeks ago. So the idea is that we want to be able to, of course, optimize for the long term, right? The expected cumulative reward or return in this case. So, but we want to be able to formulate certain desires or for behaviors to implement over a fixed horizon sometimes. Yeah. So we might say, we only want to do a lane change if this results in a certain speed up. And if it doesn't result in the speed up, then within the next 10 seconds or so, then we don't want to change lanes. Not to violate any comfort rules or something like that for the passenger. So there are many desires that you can formulate that make sense, that naturally lend themselves to be formulated in a fixed horizon setting. Yeah, but at the same time, of course, you want to integrate them into the long-term objective. Yeah, of course, you want to maximize your expected cumulative rewards while adhering to these constraints. Yeah, so I'm skipping many details, and you can find the details in the IROS paper, of course. But this is the basic setting. We have some mini batch of transitions maybe collected on a highway. We have some set of rules and desires that we want to implement, something like comfort, safety, or some special traffic rules. For instance, in Germany here, we have a keep right rule. Don't need to go into details here, but something that you need to implement. And for those, we can then formulate constraints and some cost signals that map from states to action, from states and actions to, so either some R or to some cost value for the long term, or to some fixed horizon cost. And then we calculate safe action sets for these different cost signals. All of them which should be lower or equal to some beta, which is a threshold that we can set for each of the constraints. And then we actually, use the intersection of all of these safe action sets when we calculate our targets. So we only consider actions that actually are in the intersection of all the safe sets for all the constraints, and only update with those actions. All right, and then also when we do the policy extraction from these Q values, then again, we only use these safe action sets. So real quick, how do we do this? So let's first look at the normal case, where we typically formulate the long-term desires or constraints with some expected sum of the discounted average immediate costs, just like here. That's the standard way. So here we have an infinite horizon, but then we really need to care about discounting, yeah, in order not to end up with infinite values. And that makes things difficult to really formulate if we have several reward objectives and we need to weigh them with discount factors and maybe weighting factors for the different objectives. Things can become quite messy very quickly. So what we can do is with these truncated Q functions, we can express them over a limited horizon. Yeah, so here we have a finite horizon, and here's another example where this could fit. We want to limit the agent to maybe just 2 lane changes within the next 2 seconds, again, not to violate comfort too much. And the nice thing is, if we have a limited horizon, a finite horizon, we don't need this discounting, yeah, because values will be finite if each individual cost is finite. So how could we model this cost estimation on a fixed horizon and by staying off policy still? Yeah, if we assume we don't have a model. Well, again, we use bootstrapping here, and we use a network that estimates this first cost signal. Yeah, the first head of this network estimates the immediate cost, and then the others will provide the immediate cost and the future estimation of this previous head. Yeah, again, they will bootstrap, but now it's about costs. We just use the same formalism, yeah, as we did in these truncated Q functions. We evaluated this in an experimental setup in the Sumo simulator, a traffic simulator that's open source. And where we collected 500,000 transitions, where we had an exploratory policy that did about 20% lane changes, and a simpler reward function where the agent should stay close to a desired speed, basically. And so we compared different approaches here. This was based on DQN. So this is the discrete action setting. We did DQN with regular reward shaping, where we had different reward terms and a weighting factor for things like safety, keeping right, and comfort. And also did this with additional loss terms that would implement. Don't need to go into the details, but this was a different weighting that we also tried, and we optimized both of these, with random search, doing hyperparameter optimization, or we also tried a masking approach that would always mask, after the Q functions were learned, would mask out unsafe actions. But the difference in our approach is that these safe actions are considered already during learning and not just during the policy extraction stage. And as we show in the paper, this constrained approach was with these fixed cost functions, if you like, was the one that was able to be as fast, basically, as the unconstrained or the reward shaping based approaches, but didn't do a single constraint violation. Okay, since I'm running out of time, just real quick. Now you saw the truncated Q functions, how we used it in this reward shaping, or this action space shaping, I should say. Now let me briefly talk about an inverse reinforcement learning approach that we presented at NeurIPS last year, called deep inverse Q learning with constraints, where we also use this constrained approach that I just talked about within an inverse Q learning approach. And the setting is, again, we collect some expert demonstrations here that, where we assume that the expert has some kind of probabilistic stochastic policy for the state action distribution. And we want to adhere to a set of constraints. Right, and I'm not going through the derivation here. You can find it in the paper, but the gist of it is that we come up with these terms called eta, which are based on the log probability of all the actions of the expert demonstrations minus these shifted Q functions, that I just talked about. They actually enabled us to do this in a model-free way. And then we can calculate our targets for a number of actions using this equation here, and then again use these the safe action sets that I just talked about also in this approach to implement something like, having unconstrained demonstrations, but then, learning from these demonstrations, extracting a reward function that would then also implement constraints. And we use this, so let me first talk a little bit about how to do this in a little bit more detail. So the first algorithm that we presented in this NeurIPS paper was called YAVI for inverse action value iteration. That was based on having a model of the environment available. Yeah, you can see it here in the expectation that, of course, needs the full model available. But what we can realize is that this part here is actually what the shifted Q function is estimating. Okay, so what we did then was to do sampling and then using a shifted Q function to just estimate this basically. Yeah. So together with some other tricks that we did, we need a state action visitation counter, and then use stochastic approximation in order to calculate the rewards for each sample that we get. We can then implement this in a fully model-free way. Yeah, don't need to go through the source code, but here the shifted Q functions really, or maybe we'll real quick just show the source code. Here, the shifted Q functions were important really because we need in this part of the algorithm, we need to calculate this eta for all the actions that are available. And here we really need the shifted Q function. Yeah, so doing that, we showed that when we compared with maximum entropy methods, we can be several orders of magnitudes faster and also reach better expected value differences than maximum entropy inverse RL methods. This is a little toy world example. As well as here we see it in action. So here we got expert demonstrations on the US highway at first, which were completely unconstrained. Yeah. So again, this is the Sumo simulator, and of course this is our ego car. The colors indicate the action that will be performed. So blue for left lane changes, red for right lane changes. So here it's the expert policy on the German highway. It's not doing the keeping right. So, keeping right means if you have a gap of, I think, 10 seconds on the right, where you would not be blocked by a different car, then you should actually change lane, even though everything is open and you don't have anybody in front of you. You should keep to the right. And if we use this, then with this constrained inverse RL approach, as you can see here, it will then adhere to this constraint that we showed it. Okay. Let me come to the conclusion. What I showed you is that decoupling these Q predictions for different horizon length makes it possible to adjust step sizes and also do other architectural choices maybe that you might have in mind that could be beneficial for your learning problem to do it independently. It's a generalization as we look at it of regular Q learning. And you can recover regular Q learning if you keep all the learning rates the same. I also showed you how to use these off-policy fixed horizon cost estimations based on these truncated Q functions, and how they might allow for intuitive formulation of desires and constraints that let you do action shaping, and is in our experience much easier than trying to shape your rewards with different weighting factors or things like that. So you don't need any weighting factors at all in this formulation. And then finally, I just briefly touched on how we use these shifted Q functions to enable model-free estimation of immediate rewards in this inverse Q learning. That's it for today. Thank you very much.